short background on the SYZ conjecture. So SYZ, this stands for Strominger Yau Zaslav. So I will just give a quick overview of what this is about. So throughout the talk, the setup will be the following. I will be considering X over the punctured disk. This is going to be a projective family of what I'm going to call Calabi-Yau manifolds. So I'm going to explain in just a second. Smooth, there will be smooth throughout the talk. And I am assuming that the family is meromorphic at t equals 0, which basically means that the family X is defined over the field of a formal series, which is K is C double parenthesis T. So basically, the equations of X inside projective space have equations that are meromorphic functions of T. So to me, Calabi-Yau manifold, it just means that the canonical bundle of each fiber is trivial. So this is maybe not the most usual definition, as I'm including a billion varieties as well. And so I'm going to fix L a relative polarization, so a relatively ample line bundle on my family. So due to the Calabi-Yau condition, each xt, is it fine if I write down here? Each xt comes.
Make it look very large.
Yes. Comes with is going to come with a probability measure defined in the following way. So mu t. So since the canonical bundle is trivial, there exists omega, which is the family of omega t's, relative trivialization of the relative canonical bundle. So basically, it's a family of holomorphic n forms nowhere vanishing on the fibers, and so I can just define mu t. This is I to the n squared over some constant, which doesn't matter too much, and it's just omega t wedge omega t bar. So this is a holomorphic n form on xt. So this is a smooth volume form, and I normalize everything such that the integral over xt of mu t is equal to 1. So I normalize it to be a probability measure. And so then the consequence of that is that by Yau's theorem, the following PDE, which I'm going to write, so it's IDD bar of phi Calabi-Yau t to the n. So this is a two form which is given in the following way. It's d2 phi t over dzi dzj bar times dzi dzj bar. So this is the two form. I take the nth exterior power. This is equal to mu t. And this has a unique solution up to a constant. And so this is interesting for differential geometry. So I won't be discussing this too much. But this is a positive definite two form, which just means that this matrix is positive definite, and this defines a Keller-Ritchie flat metric on xt, which is why this is interesting from the point of view of differential geometry. So in particular, what is interesting for me is just it induces a canonical distance on xt. So xt is a complex manifold, but it has a metric and so on, which is canonical in a very reasonable way, which is an object of a high interest to differential geometers. And so now, assuming that the family X is what we call maximally degenerate. At t equals 0, which I will define this a bit later in the talk, but it means that the x is degenerating in the worst possible way when t goes to 0. So it's the most possible, the most complicated case possible. Then the SYZ conjecture predicts the following. So this is a conjecture that comes from mirror symmetry, and it's originally motivated by actually physics, but I won't explain the motivations too much. Is first that we have a bound on the diameter of the complex manifold xt with the distance I mentioned above. This is the log of t to the 1/2. And then after rescaling to diameter 1, so there exists a map ft from xt to some base b. So b is going to be a real manifold of dimension n, where n is a complex dimension of xt. So this is half the real dimension of xt, such that the fibers are very small tori. So those are tori of size log t to the -1. And so the xt collapse as metric space to be endowed with some Riemannian metric, let's say. So this is what this predicts. And so at this point, a very natural question would be, what does any of this has to do with tropical geometry? And so this is what I'm going to explain in the example of hypersurfaces. So this is really a differential geometric conjecture, and the insight of Kontsevich and Soibelman was that this is very much related to non-Archimedean geometry. So am I doing this the right way? So I will just explain an explicit example. So I'm going to consider the following family, X. So this is given by this is going to be a family of hypersurfaces in projective space, and has an explicit equation like this: z0 up to zn plus 1 plus c times f. So this is a homogeneous polynomial of degree n plus 2 that I choose generic enough. So this is in Pn plus 1 times this family of hypersurfaces. So here, maximally degenerate means that when t goes to 0, this goes to the reunion of n plus 1, n plus 2 coordinate hyperplanes. So this is very far from being a smooth variety. This, in a combinatorial way, the limiting object is quite complicated. But I can also view this as a scheme over Pn plus 1 over k, where k is a non-Archimedean field of a complex Lorentz series. So a very basic idea is to look at the log of modulus of coordinates, which I'm going to write log t. So this is going to go from the ambient P1, Pn plus 1 to some compactification of Rn plus 1. Let me just write this with a bar. I'm just sending z0 up to zn plus 1. This is just going to be a log of z1 over log of t up to log of zn plus 1 over log of t. And then what we have is the Vieri-Groves theorem, is that the image of X under this map is going to converge to what is a tropical variety, which is the tropicalization of the hypersurface. So log the image by the log of the modulus of xt inside Rn plus 1. This converges when t goes to 0 to basically the tropicalization of X, but viewed as a variety of the non-Archimedean field K. So very explicitly, this is given by the corner locus of the PL function that I obtained from the equation of X. So this is very explicit. I can draw a picture. This is going to look something like this in dimension 2. So this is going to contain the boundary of so this is going to contain delta P, where P is the convex hull of E1 up to En plus 1, the standard basis, minus, and then there is another vector down there, which I'm not going to draw, up to etc. minus En plus 1. So this contains this as a bounded subset, and then it's something like this. So we have this those two planes as unbounded two planes are spanning out. So basically I have the boundary of a tetrahedron. And then I have those two planes, unbounded cells going there. And then we have the following theorem that I will state in a cleaner way a bit later by Buxom and Janssen, is that if I push forward my measure that I erased, if I look at my measure mu t from earlier and I push it forward to this log of modulus map, log t of mu t, this when t goes to 0, this converges to mu 0, where this is the Lebesgue measure on the boundary of the polytope P. So in a way, the family of measures that come from a complex differential geometry, my volume forms, when I push them down to the tropicalization, it singles out somehow the bounded part of the tropicalization. And this is going to be the B from the SYZ conjecture. So it's the boundary of the polytope.
Okay, yeah.
Yeah, so it's, for instance, so for the two-dimensional, so in general, it should be homeomorphic to a sphere. Yeah, it's the boundary of this. And so the unbounded region is not interesting from the point of view of this measure. And so the very rough idea is going to be that this map FT, in some sense, this should be a small perturbation of just the log of the modulus of the coordinates. But this is a very specific situation because I'm looking at a family of hypersurfaces. So to explain the more general picture, I need to introduce Berkovich spaces, which is going to be the convenient framework for this.
Is the measure normalized in this?
I normalized everything to -1, but mostly out of laziness. You can normalize. Yeah, there are more clever ways to normalize it, but basically the normalization should take into account the line bundle L. But yeah, normalize everything. So yeah, all the cells have an integral structure. So the Lebesgue measure is canonical here. Yeah. But yeah, I really don't want to talk about normalization. So now I want to do this basically coordinate free. All of this use the fact that I had canonical coordinates coming from the embedding into Pn. So now I want to do this more generally. So X is more generally, X is a projective variety of the field of Laurent series C double parenthesis T. And this is a non-Archimedean field with a absolute value, which is an exponential of minus the order of vanishing at 0. So from this, using the theory of Berkovich, there exists what I'm going to write as Xn. This is going to be the Berkovich analytification. So this is Berkovich analytification of X with respect to this non-Archimedean absolute value. And for now, for me, this is just going to be a topological space. So how is this? This is kind of similar to the process that if I have a scheme over C, I have a complex analytic space associated. And this is kind of a similar procedure. I have a scheme over a non-Archimedean field, which is a valued field, and I can associate it to it an analytic space, which in particular will be a very nice topological space. So very roughly, this is the space of valuations on the function field of X. So this is a compactification of the following set. This is a set of non-Archimedean absolute values. This is on the function field of X. So those are non-Archimedean absolute values. And I want them to restrict to the subfield of constant functions. They just restrict to the given absolute value. So this is and then you have to compactify this, but I won't explain how. And this has a topology which is just given by evaluation maps. So the weakest topology is such that if f is a meromorphic function on X, then what I'm going to write as a absolute value of f non-Archimedean. So this goes to X and to R, and it's just I'm sending an absolute value X, well, to absolute value, but evaluated at f. So f X. I want this to be continuous for any meromorphic function. So this is kind of a weak topology, it's just given by evaluation maps. And so now the upshot of this is that it is a very nice topological space. So just like complex analytic spaces. So let me write down. So this is locally compact. So this is first Hausdorff probably. As a topological space, this is Hausdorff, locally compact. In fact, it is compact if and only if X is proper over K, which is always the case for me in this talk. This is locally path connected, etc. So in many ways, this is topologically kind of like a complex analytic space. We can do a measure theory and such things on this space, which is quite convenient. And as I'm going to explain right now, it encodes like tropical information about X. So I'm going to explain how. So let me start with a definition. I'm going to say that X over R is so I'm going to write R as the valuation ring of my non-Archimedean field. So here this is just C double bracket T. I'm going to say that this is a model of X. If so X, I'm asking it to be flat and regular. So you can just imagine that it's smooth, for instance. And so the generic fiber of X is just my given family X. So from the complex geometric perspective, I'm just extending my family over the disk. And I will furthermore say that X is SNC for simple normal crossing. I don't know if you can see this is readable or not. If X0, so this is the fiber over 0. So over C. So this is what is over the over 0 inside the disk. Is let me write this as X0 is sum over I of the AI DIs, where those are smooth intersecting transversally divisors. Intersecting. So the upshot of this is that if I have such an SNC model, I can associate to it a combinatorial object, which is going to be the following thing. I'm going to write this D of curly X. This is the dual complex. So this is a cell complex encoding how the DIs intersect each other. So I won't give the formal definition, but I will explain how it is constructed. So if DI is an irreducible component of X0, just associate to it a vertex VI. This is going to be the vertex, a vertex of my dual complex. And then for each connected component of a DI intersected DJ, what I'm going to do is I'm going to put an edge EIJ from VI to VJ. So basically, this is a dual complex whose faces are in bijection with the intersection of components here, except it reverses inclusions. So I can draw a picture, for instance, for this one. This is so if, for instance, X0 is a subset of C3, and it just as before is given by the reunion of coordinate hyperplanes. So this is Z1, Z2, Z3 equals 0. So this is the unions of 3 copies of C2 intersecting transversely. So I'm going to have 3 vertices, V1, V2, V3, corresponding to the irreducible components. Then maybe I'd draw the normal picture first. So this is those three coordinates hyperplanes. Then so Z1 equals 0 and Z2 equals 0, they intersect along a line. Then those two intersect along line 2, and here I have a line 2. So between any pair of vertices, I put an edge. And then there is a triple point here where all three lines intersect. So what I do is I just draw a two cell between those three edges. And so the upshot is that D of curly X is so it's a cell complex of a dimension lesser than n, where n was a dimension of X. And so the very rough idea about the Berkovich space is that it's a way to encode all of those dual complexes. So there are many models. If I start from a model, I can get another one by blowing up some closed subvariety of the special fiber. So it's really something that is non-canonical. But basically, if I take all of them and consider all of the dual complexes, what I get in the end is a Berkovich space. So we have the following properties. If I have a morphism between two models of X, so I can write this as, say, P, such that when I restrict it to X, this is just identity, then this induces a piecewise affine map between dual complexes, so from D of curly X prime to D of curly X, and this is somehow a contraction. So I'm not going to prove this, but I will explain on a picture. So for instance, if this is X0 and I blow up, say, this point, so here the dual complex is just, I have two vertices joined by an edge. If I blow up this point, I get something like this. This is X prime 0. What I'm adding is just, I'm adding a vertex and an edge here. And so the map P is just given by, I'm contracting this edge.
This is always a homotopy equivalence or not? If the multiplicity is
Yes.
one, I'm not sure. Yes.
Yeah, yeah. I mean, the multiplicity doesn't change anything topologically, basically. So. And so, yeah, this, as Antoine mentioned, this is always a homotopy equivalence, but this is not super relevant for me. Basically, I mean, basically every map like this is kind of a sequence of blowups, so it's just you're contracting some centers. Then to give another example, if I blow up this point, once again, I'm adding an exceptional divisor here. But this time, actually, the map between dual complexes is just the identity. And what I did was subdivide the edge. So here, this map is just the identity. There is also a transitivity property that I'm not going to write down. If I have three of them and two maps, then the compositions are the same. But what is actually interesting is that while for now, those are just abstract dual complexes. But in fact, they have a natural geometric realization inside the Berkovich space. So basically, what this means is that we can think of the points of the dual complex as valuations. So we have the following fact that for curly X, the dual complex embeds naturally inside Xn. And so the image, by definition, we call this the skeleton of a curly X. This is a skeleton. And in some sense, you can think of this as a finite approximation. So basically, we're approximating the Berkovich space by just a finite dimensional cell complex. And what did I want to say? And conversely, there exists a retraction the other way around from Xn to this image. So this is what we call the Berkovich retraction, which is indeed a retraction of this inclusion. That is, if X is inside a skeleton, then rho curly X of X is equal to X. And so what we get is the following theorem. Maybe I can explain. No, maybe I won't have time to explain, but no, I can explain very briefly. What this means is that we are viewing points. We can view points of curly D of curly X as valuations on the function field of X. And the way this is done, let me just explain it for the vertices. If Vi is a vertex of the dual complex, then we view it as a valuation order of vanishing of Di. So this is a valuation on the function field of the curly X, but this is those two schemes are birational. So the order of vanishing of along the irreducible component Di is indeed a valuation on the function field of straight X. And then we can interpolate between those, which I won't explain.
Can you clarify the notation, right? This K without the star and with the star?
Yeah, no, it's just yeah, because okay. Sorry. Yeah, it's just that it's because here this is it depends if you view it as a valuation or an absolute value, I guess. But if this is a valuation, this should be like this. And so the end result of this is that we actually get the Berkovich space as the inverse limit of all skeletons, at least as a topological space.
Do you need a simple normal crossings for this result?
So which one?
The fact that you have this fraction again?
So to define the dual complex, you need some regularity on the model, but the correct condition would be DLT, divisorially log terminal. Basically, the model has to be SNC at least at the generic point.
Not, I mean, normal crossing is sufficient. Simple, you don't care, I think, because you can.
This is fine. This is fine. But then to define the retraction, this is defined using valuations and local equations. So what you need is that the components of the special fiber are Cartier, and this is actually important. And otherwise, yeah, there are like the example of hypersurface I gave earlier doesn't have a retraction, because it has some ordinary double points along the special fiber. So some divisors are not Cartier, and you cannot take a local equation, and you cannot define the retraction.
But if the skeleton is not defined, if the special fiber is too...
it's not defined in the sense of Berkovich, yes. But it's in this case, it's DLT. So Niquez and Shu prove that you can still define it. It's just not a Berkovich construction, yeah. So the upshot of all of this is the following theorem. So this was stated by Kontsevich and Seubelman, but I'm not sure this is the optimal source, also because I just stated it without proof. Is that in fact this realizes the Berkovich space as the inverse limit over all the SNC models of those skeleta. So let me draw a picture. For instance, if xn is an elliptic curve over C double parenthesis T with a bad reduction. So then there is going to be a model whose special fiber is a cycle of rational curves. So this space is going to contain a circle. And then over each rational point of the circle, you're going to have an infinite graph, something like this. So notably, the space is a homotopy equivalent to a circle. And you get something, some picture like this. And this is actually still compact because the opens are fairly big. This is not the usual graph topology here. So then this is a picture of XR. So now we're going to use this space to extend our, so let me get back to the original setup where I have my family of a complex manifold over D star. And so then I have this Xn, this Berkovich space. And we want to see this as an asymptotic incarnation of the complex analytic fibers. So of the XTs. And the way this is done, at least at the topological level, is we define the following space. This is what we call the hybrid space. So as a set, this is pretty simple. So this is going to come with a map to the disk. So I take my family of complex varieties, which is over the punctured disk. And then I'm going to extend it across 0. And what I'm going to do is I'm going to put this space, this non-Archimedean analytic space over 0. So for now, this is just a very weird looking set. Except I can put a topology on this in a natural way. So the topology is defined in the following way. If U inside of X is a Zariski open, and F is a holomorphic function on U with no zeros, then I require that log of F divided of log of T. So this lives on the complex analytic part. So this is a complex analytic expression. Extends to this hybrid space through the evaluation map from earlier. So F is notably a meromorphic function on X. So this extends via the evaluation map that I denoted log of F non-Archimedean earlier. So I have here I just take log of modulus of F rescaled by log of T. And I want this, when T goes to 0, to converge to log of modulus of F, but in the non-Archimedean way. So for now, this is just a topological space, and it will actually remain so. But now we have the following generalization of the theorem I mentioned earlier. So this is from Buxom and Janssen. This is from 17. So if X is going to be a family of Calabi-Yau manifolds, which I'm just going to write as cy. As before, mu t is the modulus square of the holomorphic n form that I normalize to have a mass 1. Then the mu t converge weakly when t goes to 0 on this hybrid space. So this is a family of measures on the hybrid space, and when t goes to 0, they converge to a measure mu 0. So this is supported on the fiber over 0, which is this Berkovich space. But in fact, we even have better, is that mu 0 is a Lebesgue measure. So I'm being a bit vague here. Actually, on a skeleton, which I'm going to write as skeleton of X, which we call the essential skeleton, which has dimension, then again, smaller than the dimension of X. So this is exactly the result I was mentioning earlier, is that those measures converge in this hybrid space, which is completely general and independent of a choice of coordinates, to a Lebesgue measure on a cell complex, which is exactly the picture I had earlier, where I had this tropicalization, and it would go to the Lebesgue measure on the boundary of a polytope. And this is in fact the same result. And so then this suggests that this should be the base of the SYZ fibration. And so in a way, this is a piecewise affine object that is very much related to tropical geometry. And so let me just give finally the definition of what it means to be maximally degenerate. So X is maximally degenerate if this essential skeleton has a maximal dimension. So if the dimension of this essential skeleton is n, which is the biggest possible dimension. So it means that from a tropical perspective, the fibers XT break into as many pieces as possible because their dual complex is going to be of a dimension as big as possible. So for instance, this is the opposite case. This is as far as possible from the case of potential good reduction. This would be what it means.
Then the skeleton would be one point.
Yes. Yeah, it's always connected. So now I have maybe 15 minutes left to talk a bit about pluripotential theory. So now at the level of measures, we have a satisfying result. But we want to enhance this a bit to yes.
Whether there's a way to put weights in the top dimensional cells, this skeleton, to make it balanced in the sense of tropical geometry?
My expectation would be no, suggested by this example, where basically you have a weight, because this is a 2-cell. In this case, this is realized as a 2-cell inside the tropicalization, and it does have a weight. But if you write the balancing condition, it involves also the unbounded edges. So there is, like here, for instance, those have 4, this is 1, and this is 4, and this is 4. And you can write down the balancing condition, but it involves the unbounded edges. So I wouldn't expect that you can balance the skeleton. And this is actually an issue because we want to do we want to define a notion of convex function there, and it's actually pretty hard to do.
Well, it's not embedded in the vector space. So
Yes. Yeah, but even in the case where we have a natural embedding inside a vector space, basically the balancing condition involves some faces we don't see. And those are, in some sense, they behave poorly from the point of view of differential geometry, because the whole Calabi-Yau measure is supported here. Like this has very small measures, so in some sense it's negligible. So asymptotically, when t goes to 0, you should lose this balancing. So recall that our original motivation was this Keller-Ritchie flat metric, which was I dd bar of phi t. So this was a positive 1-1 form, and such that omega t, maybe I write this as I dd bar phi t to the n was mu t. It was originally this PDE that we want to understand how this behaves asymptotically. And so the idea is that we're going to cook up a similar theory on this Berkovich analytic space. So phi t is such that, so it was the matrix of the second derivatives that was positive. dZij bar. This was a positive matrix, and this is what it means. It means that phi is this is what we call a plurisubharmonic in a complex geometry. And so the idea is going to define. So I'm going to write this always as PSH. PSH functions. So strictly speaking, they are not functions, but I'm going to pretend for the talk. On this Berkovich space Xn. There are metrics on the line bundle. Oh. So in the complex world, locally, it's a function. And here, it's a bit more complicated, but I'm just going to pretend that those are functions. So don't be offended.
But they live in the line bundle L.
Yeah, it's everything depends on the polarization.
Yeah. So L doesn't appear explicitly in your talk, but implicitly it is.
Yeah, it's hidden there. So the first basic piece is that we're going to define a PSH model function. So this is associated to a model. So I'm going to take a model curly X together with curly L, where L is a line bundle on curly X, such that when I restrict it to the open part X, this is just my original line bundle. And I'm going to want it to be nef. And so the associated function phi L, so this is not really a function, but when I evaluate it at the valuation X, this is a Vx of a SL, where SL is a local trivialization of the line bundle L at X. So it's not really at X, but let's pretend it is. So this is minus log of SL. So this would be the what we call a piecewise affine PSH function. So this function phi L, it satisfies the following properties. So this is a piecewise affine function on each skeleton inside Xn. So in a natural way, this is a piecewise affine function. And also it actually factors for the retraction associated to the model curly X where it lives. So it actually factors through a finite dimensional cell complex. So it is actually not that complicated. Despite the quite abstract definition, it's actually a piecewise affine function on a finite dimensional cell complex. And then the general definition of a PSH function is more complicated because we have to do uniform limits. So a PSH function on Xn is a uniform limit of a PSH model functions. And so the issue here is that say, if I write phi as a uniform limit of the phi k's, then phi k comes from each phi k comes from a fixed skeleton of x curly xk, but this is getting bigger and bigger as k increases. So this doesn't actually factor through a finite dimensional cell complex. So maybe I can do the picture from earlier again. For this elliptic curve. So basically a PSH model function, this would be a convex function in the sense of graphs on a finite graph like this. And then you extend it to the whole space using this retraction rho curly x. But then when you take a uniform limit, it actually doesn't factor to a finite. It's not a convex function on a finite graph anymore. So it might branch out infinitely somehow. So it can be a quite complicated object. So now the whole point is that we can actually define if phi is a PSH function on Xn, we can define its Monge-Ampère measure, which I'm just going to write mi of phi. So this is an analog thing to this process from earlier where I was taking I d bar to the n. So this is going to be a measure on this analytic space. So I'm not going to explain how it is defined, but it has an explicit definition for model functions, and then we can extend by passing through the limit. And so now the basic idea is that since my Lebesgue measure earlier from mu0 was the limit of the mu t's when t goes to 0, the solution phi to the non-Archimedean Monge-Ampère equation, Monge-Ampère of phi is mu0. This should be the limiting object of the phi t's of the Calabi-Yau matrix. So basically, we have a quite abstract object, which is somehow an infinite limit of piecewise affine functions on this space. And this should encode the asymptotic of the solution of my PDE on the complex manifold. So I have 5 minutes to finish. So now we have the following recent theorem by Yang Li. So let phi be the unique PSH function on the Berkovich space on Xn such that Monge pair of phi is equal to mu0, my limiting measure, and assume that there exists models curly x of x such that phi actually factors through this retraction map, not over the whole skeleton, but over the interior of the top dimensional faces of the skeleton. So basically, we want this. This is a function on the Berkovich space, which is very large, and we wanted to factor through some. Here, this would be some finite graph. Very roughly, we wanted to factor through to come from a function on a finite cell complex, and then we have a weak form, which I'm not going to write in detail because I don't have time, of the SYZ conjecture. Conjecture actually holds. So I'm not going to write it down explicitly because it's a bit weaker from the statement I gave earlier. But one thing worth noting is that this assumption star, this is something that is purely lives on this non-Archimedean analytic space. And the outcome is a conjecture in differential geometry. This is a completely differential geometric statement about the exact existence of some vibration, which is very rigid, which is a very hard question in general. And we have reduced it to a question in non-Archimedean geometry, basically. That we have some object on an infinite limit of cell complexes, and we want to come from a finite tropical object, basically. And so when this was, when Yang Li posted this, there are actually no example outside of a billion varieties where we were able to check this assumption. And a billion varieties are a bit too specific of an example. And so recently we made some progress in the hypersurface case. So to finish, I will just finish by stating this. So this was done independently by myself and Huldren, Janssen, Amazon, Matt Cleary, and myself, using actually a different, quite different argument. So I'm going back to my family of hypersurfaces. This is a Z0 up to Zn plus 1 plus T Fn plus 2 of Z equals 0. So this is inside Pn plus 1 times the disk. Then there exists a convex function U, this is just a convex function on Rn plus 1, such that if I'm going to write psi of x, so this is going to be a function, so psi, this is going to be a function on the analytification of a projective space, Pn plus 1 an. So psi of x, this is going to be u, but applied to the log of the modulus of the coordinates at x. So this is u of log of z1 non-Archimedean up to log zn plus 1 non-Archimedean. So this is a convex function in the log of the modulus of the coordinates. Then then the phi from up there. This is the restriction of psi to x. So not only does this function psi come from is actually the restriction of a function on the projective space, but this is also a toric function, in that it depends only on the log of the modulus of the coordinates. So in more seriously, this is a restriction of a toric metric on Pn plus 1. And so then this is relatively easy, is that we can check using this explicit expression, we can check the assumption star in the hypersurface case. And before I finish, I should just mention that we can do something similar when we replace Pn plus 1 by a toric Fano variety, and we take a family of hypersurfaces in a toric Fano variety. Then there are actually examples where this is false. So this is going to be wrong for at least 1/3. So the toric Fano variety comes from a polytope. You can look at the classification of 3-dimensional polytopes. There are roughly 4,500 of them. And this is going to be wrong for at least 1/3 of them. So this uses the fact that Pn plus 1 has a lot of symmetry. So this is very specific. And I should probably stop here.
Okay.